This man is Al-Battani, and he stands between the earth and the heavens, not as a priest, but as a measurer.
The year is 880.
The city is Raqqa, a pearl on the banks of the Euphrates.
This is the heartland of the Abbasid Caliphate, a civilization drunk on knowledge, where the ink of the scholar is in its libraries. The ghosts of Euclid, Archimedes, and Ptolemy speak in newly translated Arabic.
Yet their voices, though revered, are echoes from a distant past.
He is an architect of the unseen, a cartographer of cosmic time. Around him, the world of astronomy is a magnificent but flawed inheritance. It is a Greek temple built on aging foundations, beautiful in its geometry but trembling with inaccuracies. Al-Battani senses this instability not as a failing of the ancients, but as a sacred duty for the present. The universe, he believes, is a text written in the language of mathematics, a perfect creation of a perfect creator.
Any error in its description is not a flaw in the design, but a failure of the human observer.
He is here to correct the grammar of the cosmos. This single mind, poised between ancient wisdom and empirical truth, is about to build a... Before him, the universe was Ptolemy's.
For 700 years, the Greco-Roman astronomer's Almagest was not a theory, but celestial law.
It was a staggering work of genius.
It was the best account of the heavens humanity possessed, and it had guided Roman engineers, Persian astrologers, and Byzantine sailors. Yet, it was a machine groaning under the weight of its own complexity and the slow accumulation of time.
The sky was no longer where Ptolemy's tables said it should be.
The calculated positions of the sun, moon, and planets were drifting, like a ship whose navigator is using a faded centuries-old chart. This was more than an academic problem. For the civilization that produced Al-Battani, precision was an act of faith.
The direction of Mecca for Dale prayer, the exact moment of the new moon to begin Ramadan.
The Greek system, based on cumbersome geometric chords and observational data from Alexandria.
It was a venerable relic, not a living tool.
The intellectual crisis was silent but profound. If the heavens, the very symbol of divine perfection, into this world of elegant but decaying certainty, Muhammad ibn Jabir ibn Sinan al-Battani was born. He hailed from Haran, a city with a mysterious, ancient pedigree of Sabian star worshippers.
His father was a maker of scientific instruments, a craftsman who shaped brass and wood into tools for seeing the unseen.
Al-Battani thus grew up, not merely reading about the stars, but holding the means to measure them in his hands. He inherited a dual legacy: the deep spiritual reverence for the cosmos from his homeland, and the rigorous.
He was the answer to a question his civilization was desperate to ask. Can we know the heavens? His revelation was not a single, blinding flash of insight, but the patient culmination of... It was codified in a masterpiece known as the Kitabul Zij, or the Book of Astronomical Tables.
Later, when it reached a hungry Europe, it would be known as De Scientia Stellarum, on the science of the stars.
The title itself is a quiet revolution.
A Zij was a common format, a handbook of celestial data.
But Al-Battani's was different. It was not a mere commentary on Ptolemy. It was a correction. It was an audit of the heavens. It moves with deliberate, unhurried precision across a sheet of parchment, leaving behind the elegant curves of Arabic script. The ink is a deep, rich black,
to a matte, burnished gold, as if the knowledge itself is illuminating the page.
where the Greeks, including Ptolemy, had used the geometric system of chords, the straight line instead of a clumsy chord. The sine relates an angle directly to the ratios of the sides of a right-angled triangle.
With this, he also introduced its relatives, the cosine, the tangent, and the cotangent. With this, he also introduced its relatives, the cosine, the tangent, and the cotangent.
This was not just a change in terminology. It was like upgrading from an abacus to a mechanical calculator. Trigonometry, in his hands, became a sharp, elegant scalpel for dissecting the motions of the heavens. He dismantled the old universe and rebuilt the cosmos on a foundation of mathematical truth. He took Ptolemy's data for the length of the solar year, and after decades of his insomnia, he was off by a mere 2 minutes and 22 seconds from the modern value. He recalculated the precession of the equinoxes, the slow wobble of Earth's axis, and proved Ptolemy's figure was nearly 40% wrong.
He demonstrated that the sun's apogee, its first point from the Earth, was not fixed, as Ptolemy had insisted.
Knowledge sealed in a book is a seed in a vault.
Al-Battani's genius was in its application, transforming abstract numbers into a practical mastery of time and space.
His observatory at Raqqa became a laboratory where theory was forged into fact. It housed instruments of a scale and precision previously unknown, including a massive mural quadrant.
These were not the portable astrolabes of his predecessors. They were monumental engines of discovery. He stood on the shoulders of the Greek giant Ptolemy, using a mathematical language refined from Indian sources.
He was not a solitum genius.
He was a product of a civilization that patronized science, where caliphs funded observatories and translation.
His contemporaries, scholars like Thabit ibn Qurra and the Banu Musa brothers, were part of this grand intellectual ecosystem.
Disciples and fellow astronomers absorbed his methods, and soon, copies of his Zij began their slow, inexorable journey.
They traveled along the trade routes of the Silk Road, were carried across the sands of North Africa.
There, on the frontier of Christian Europe, his numbers waited. The transcendence began with translation.
In the 12th century, in the vibrant intellectual melting pots of Toledo and Sicily, Al-Battani's Zij
now known as Albategnius or Albategnius, his mind crossed the civilizational divide. What arrived in Europe was not just a set of tables, it was a methodology.
It was a demonstration that the sacred texts of the ancients were not infallible, and that direct observation could reveal a deeper, more accurate truth. Underneath it, a faint, rhythmic, mechanical ticking emerges, like a complex clockwork mechanism or a primitive calculating machine.
The soundscape suggests the birth of a new, mechanistic view of the...
4 centuries later, a Polish canon named Nicolaus Copernicus would study De Scientia Stellarum intently.
He cites Al-Battani 23 times in his own revolutionary work, De Revolutionibus Orbium Coelestium.
He cites Al-Battani 23 times in his own revolutionary work, De Revolutionibus Orbium Coelestium.
It was Al-Battani's more accurate value for the solar year and the precession of the equinoxes that gave... Without Al-Battani's corrections, Copernicus's model would not have aligned with observation. The revolution might have stalled.
The chain reaction continued.
Tycho Brahe, the great Danish observer, revered Albategnius for his observational rigor.
Johannes Kepler used his trigonometric foundations to finally deduce the elliptical or planets. Galileo, in turn, would point his telescope to the sky, confirming the new cosmos that Al-Battani's data had helped to birth. The refined trigonometry he championed became the bedrock of the new physics. It was the language Newton would use to describe gravity. the tool engineers would use to build cathedrals. His mind had provided the scaffolding for the European scientific revolution. What then is the deeper legacy of a man who spent a lifetime gazing at specks of light?
It is the profound philosophical truth that systematic, empirical inquiry is the engine of human advancement.
To measure the world honestly is to appreciate its true majesty. To measure the world honestly is to appreciate its true majesty.
He worked in an era when knowledge was a form of light, a sacred duty to dispel the darkness of ignorance and assumption. He did not reject the wisdom of the past. He honored it by testing it against the unforgiving reality of the present.
When knowledge was light, humanity advanced. When superstition replaced reason, the flame dimmed.
The meticulous, almost devotional patience of Al-Battani. He did not seek to bend the universe's beliefs.
His legacy is a call to action, a reminder that the great made by shouting the loudest.
The man himself is
His
long
observatory
gone.
on the Euphrates
His
has
body
vanished,
returned
its
to the
brass
dust
instruments
of
melted
Mesopotamia.
down, its records turned to fragile fragments.
But the architecture of his thought remains.
It is timeless and invisible, embedded so deeply in the foundations of our world that we no longer see it.
It is there.
It is in the GPS satellite that calculates your position using spherical trigonometry, and he helped perfect.
It is in the engineer's equations that designed a bridge or a skyscraper.
It is in the algorithms that process light and sound waves, turning them into the digital fabric of modern life.
His greatest contribution was not a number, but a principle, that the universe is knowable. He taught humanity how to ask questions of the sky. He took the received wisdom of the ancient world, honored it, tested it, and ultimately surpassed it. He is not in Baghdad's gilded house of wisdom, but here, in his private observatory.
His work was a testament to the Abbasid synthesis.
The core of its power lay in a profound shift in mathematical language. This spirit represents a pinnacle of civilizational confidence.
This was a dangerously empowering idea for a continent still in its intellectual slumber.